On behalf of Phoenix Integration, welcome and thank you for joining us for today's MBSE partner session entitled Engineering from Architecture to Analysis and Design, a practical look using GENESYS and Model Center. This event is part of our 2021 virtual event series featuring industry and technology keynotes, panel discussions, workshops, knowledge seminars, and application demonstrations. This series includes over 30 sessions presented by industry and government leaders covering a range of topics, including multidisciplinary analysis and optimization, model-based systems engineering, and digital mission engineering. All sessions are free to attend. Join us as we bring the experts straight to your screen in live and interactive events. Visit the Phoenix Integration website or follow the links in your email for more information on upcoming events. And now I will take a few minutes to introduce Model Center. Model Center is the conductor for your engineering organization, coordinating all the different tools your team uses, keeping track of the work in progress, and helping everyone collaborate and stay in sync. Model Center is the framework to help you get the most out of your engineering activities, enabling your teams to get the work done more efficiently and effectively. Model Center Integrate drives productivity, allowing you to automate your software tools and tie them together across the network, whether locally or globally, into an automated workflow. Model Center Explore drives innovation, exploring your design space and viewing design alternatives to deliver the best solution. And Model Center MBSE connects MBSE systems models to engineering analysis, validating system requirements throughout the design cycle. This unlocks the promise of MBSE. And looking at this next slide, you can see an example of a lot of organizations that are using either one or all of these different capabilities of Model Center. We are pleased to work with our partner Vitech to integrate engineering analysis with the MBSE systems architecture model. This allows system engineers to validate requirements throughout the product lifecycle and design better products. For today's program, we have 3 presenters. Mr. David Long is the founder and president of Vitech. For almost 30 years, he has focused on helping organizations around the world increase their systems engineering proficiency, particularly in the areas of MBSE and digital engineering. An NCOSE fellow and expert systems engineering professional, David was the 2014-2015 president of NCOSE. Our next presenter is Mr. Steve Cash. As a principal systems engineer of professional services at Vitech, Mr. Steve Cash provides consulting and training support for Vitech customers. Steve has spent 25 years plus developing his systems engineering skills through product development in the automotive industry. He holds a BS in electrical engineering from the Marquette University, in a systems engineering professional and a graduate from NCOSE Technical Leadership Institute. And our final presenter is Mr. Alexandre Luke. Mr. Alexander Luke, an application engineer with our own Phoenix Integration. And now it is my honor to present and hand things over to Mr. David Long. Over to you.
Very good. Thank you, Jamie, for that wonderful introduction. So I'm going to try to set the stage for Steve and Alex to give more detail. If we talk about delivering today's complex systems, we know that it's essential to do every step of the engineering lifecycle properly. Conceptual design through model-based systems engineering, detailed design with model-based engineering, multi-domain analysis and optimization to ensure that we are engineering with rigor. But the engineering lifecycle, much like the systems that we build, relies not only on the parts, but on the interconnects. And so if we do each one of these steps excellent in isolation, but we connect these steps with the most common engineering tool in the world, Microsoft Office, the inevitable outcome is delays and defects in the products that ultimately reach the field. The approach that we take at Vitech is centered around what is the essential information that we need, not only at the systems engineering phase, but throughout the engineering life cycle to properly architect and engineer these systems. You can call this an information model, a meta model. Regardless, it is the fundamental information we need to be successful through life. We set the stage in concept, we feed that concept to model-based engineering and MDAO. This is a scalable and tailorable language. It's a natural language for systems engineers. It's not a coded language to figure out. And it's a very simple set of concepts. It helps bind together not only the architecture, but also the team. In the early stages, we talk to users and customers and stakeholders through the techniques of use cases to elicit the right requirements, to ensure that we are actually solving the right problem. In the middle of the engineering phase, we are specifying the design envelope as encoded in the architecture so that we can feed that information as the starting point for detailed design to ensure that each part is built properly with knowledge of the interconnects, with knowledge of the requirements that they're linking back to. And it's not good to architect in isolation. We need to engineer with rigor. And here we bring together the constraint definitions and all of the key design parameters through a tool such as Phoenix Model Center MBSE to ensure that at a detail, at a high fidelity level, what we have architected can actually be brought together in reality. Now, this is the information model, the fundamental philosophy that underpins what we do at Vitech. GENESYS then leverages this in three primary ways. It allows the systems engineering team to capture what they are doing and why they have done it, from first expression of need all the way through architecture and verification. At the system level, it gives us a complete picture of problem and solution. We know that we deal with a transdisciplinary team. We need to communicate with many different people. So GENESYS is all about taking that information and allowing the user to visualize your information your way. If you prefer to draw an activity diagram, but then you wish to see the interactions via a sequence diagram, simply click, open the view, auto-generate, update your model, continue. GENESYS keeps all of those artifacts in sync so that you can focus on the engineering and allow the tool to generate the artifacts. And lastly, we have to integrate that architecture with design and with analysis. The architecture in isolation, valuable, but not nearly as valuable if we can flow it through the engineering lifecycle. And as I said earlier, engineer with rigor with tools such as Model Center to confirm that architecture can in fact be realized. That's the top level. That's setting the stage. Let me turn it over now to Steve to show you this concept in practice. Steve, over to you.
Thank you, David. So David has set the context for us in describing exactly how we're going to put our information together to create that system view. What I'm going to do is go through the process and show you how to create the information, add it to the model, and get to the point where we can hand off to our detailed design teams and our analytics teams, at which point I will hand over then to Alex Luke to show you the analytical side of the interface. So I'm going to take you quickly through a systems engineering approach, through the requirements and some requirements refinement, building of a system context, and then developing that system context, the problem space requirements, and then into our behavior, and ultimately move into the parameters and constraint definitions, which will drive the analytics. So let's talk about the systems engineering approach quickly. is we fundamentally focus on problem space and solution space, where the problem space is where we're working through our requirements, our understanding of the problem, and evolving from that into our solution space. If we look at this in a little more granular detail, it's taking that enterprise perspective, the operational architecture, how things work, tying it to this black box definition, so a view of what our system is and what it interfaces to, developing then our behavior in that glass box perspective, not only looking external but internal, and assigning that behavior onto our physical architecture. If we talk about this in terms of what we typically see as in the meta model, we talk about requirements, we talk about the behavior or functions, and architecture components of just that, components. The journey is to start with requirements, where we'll use our use cases to elaborate our requirements further, and that'll be the black box view of the use case. And then we'll go to the glass box view, where we start to talk about the functionality. What are we doing? Where are we doing it? And ultimately, that will drive to our system behavior. Along the way, we'll document that journey with concerns and risks. And then we'll go through the process of allocating to the architecture. Now, we're not going to be able to go through this in full detail. We'll do it kind of in conceptual steps and give you an idea of how this process works and what it looks like. So we'll start with the idea of capturing requirements. And we're going to do this specifically for a remote control video drone system. So your typical drone that you go out and take photographs with. It starts with that set of marketing requirements. And here we can look at some of those requirements, be it cost, be it flight time, be it replaceable battery. Any of those requirements come to us in some sort of source document. We'll start with capturing that as a entity within GENESYS, so that we always have a reference back to where we started. This is the starting point, and everything ultimately flows back there. We then will take these requirements and further expand them into individual requirements that we can then show throughout the design how they trace to functionality, components, verification, etc. And in this case, I've shown both in the terms of a requirements diagram, as I have my document, and those individual requirements. Essentially, this is what it would look like in GENESYS after I have created the entities, such that I have the document and I have traceability back to that document for each requirement. Now, as we know that requirements aren't often very good, we all ultimately have to work on them and evolve them. In the case of our specifics for the video drone, the requirement of needs to fold into a travel bag is one of those. It really is quite vague. Having some cursoring problems here. Let me. So the requirement is vague, needs clarification. So we would go back then to marketing at that point and work on clarifying that. We generate a concern in GENESYS to capture that concern before we go back to marketing, so that we can ask the question, make sure we understand what the question is that we're asking. So in this case, what does this really mean that I need to fold into a travel bag? The way this relationship looks like based on the meta model is just this, is the requirement generates this concern. We continue to evolve that particular requirement. We talk to marketing and it results in a new requirement. And again, this particular requirement expands upon that idea that it folds, but it's around the idea that the user can transport the system. And I don't want it to interfere with their normal activities. And ultimately that word compact enough becomes abstract and obscure. So again, if we talk about the journey, my concern resulted in a new requirement. And you can see this, and it's captured within the meta model to show that journey. We identified that requirement is not sufficient. I can generate another concern to continue the capture of that journey. In this case, we'll go back to marketing and request a market study to further understand really what is the goal of this folds into travel bag requirement. We really want to get down to the details. So again, I can capture that documentation with a document entity in GENESYS that shows then this is where the information is from marketing, and tie it into the overall flow of the data so that we have that traceability. I've got a concern that, again, is documented by that trade study. This ultimately ends in a new requirement again that gives us very specific dimensions for that travel, folding it into that travel bag so that the user can use it. And this flow can now be displayed as that design journey. If for some reason somebody comes back and ever asks the question about how did we get here, I've got the full path. I've got that documentation of the journey. Somebody can read through this. It is the natural language that allows us to be able to read this and have knowledge. So once I've gotten my requirements captured, we're going to move into starting to define that system context. So if you remember the flow, this is that black box view of the system. And I'm going to capture that in this case, a physical block diagram is how it was captured. I not only did it as a block, but I used an image to give us some idea of what that system looked like. What you don't want to do is stop here, because this only defines our boundary. What's missing from this is what do we interact with? And so as you build the system context, you also want to point out what are those items, those external entities that I interface. In this case, it's the GPS, the user, the operational environment. We don't want to have everything in the environment in there, but enough that we understand what we're interacting with. And then finally, we want to connect all those things through links so we understand what are those connections, both from a physical instantiation, but also from what is the information, what are the physical connections, the interactions between those components. Because it's really this context enables the clarifications of those interfaces and those interoperations. Now, we'll move very quickly then from having a context to talking more about use cases and how we develop further requirements, as well as define functionality. The use cases mimic essentially that system context. We see the system as a box, and we see the external actors. We fill in with these abstract operations. We really don't have a knowledge of the solution completely. We serve it, and it serves for us to help refine both the problem space and requirements, but also to start to conceptualize then what is that behavior? What does the solution start to look like? In this case, I've identified a number of use cases, be it identified target, deliver image, charge system. There are different use cases here. Again, I'm going to use these to define behavior threads where we can explain each one of these in terms of who does what and what is the sequencing of those events to lead up to the functionality. Again, this is not a full inclusive list of all the use cases. We could add a whole bunch more. Other examples here is, what does that identify look like in the rain? What does it look like under high wind speeds? How do we manage our flight range boundary? There are a lot of different use cases we could add to this. So we're going to go through the process of developing then the behavioral threads, and we'll do this for each use case. The goal here is to define that kind of sequential set of functions that describes how the operation works. In this case, it was the system charging function that I chose to, as an example, to talk about. And it simply goes through the process of, I connect the system to the charger, I provide some connection feedback, I plug the system in, I indicate that we're charging, the user acknowledges that charger status, charge the system, again, acknowledge that it's charging, indicate the system is charging is complete, acknowledge, unplug the system charger, acknowledge that the power's gone off, disconnect the charger from the system. So that's kind of that sequential thinking of how you would charge the system. Now, when we get to the to go a little bit further with this behavior development is to then start to talk about the interactions of those functions. What information is exchanged between each step? In this case, I was very specifically looking at the idea that, hey, when I plug the charger into the system, I want the user to know that it's connected. There's a firm connection there. So this system charger connection feedback could be something along the lines of a mechanical interaction that the user feels. And then the system charging status, some way that the user knows what is the status of the charging. So we define those interactions. The last step in the thread is really being sure we understand who's doing what. Is it the user? In this case, the video drone. And you have a clear definition of what functionality falls where and what do I have to implement then in my design. Now, after I've developed all of these behavioral threads, not just this one, we'll need to take those back and integrate them into a full functionality of the system. And as we do that, we can start to identify natural boundaries that'll lead us to a physical architecture. Now I'm going to move pretty quickly through the physical architecture as I described the system context. This is the highest level of the architecture. It gives us that black box view of our system and the external actors that we interface with. This is a BDD diagram, so it's very much like the diagram I showed early. It's just a different way of looking at it. It shows only the hierarchy of the components in it. As I move down a layer, I explore then the system of interest, the video drone system, and I start to do the same thing as to break it down. Now we would use behavior as a way of breaking down these into their components. So we have the BDD that shows the hierarchy, but then the physical block diagram on the other side shows then interaction between the components. So you can get a full understanding of what are my components, how do they start to interact. I can take this down another level if I were to look specifically at the drone design and list out its components as well. This becomes the glass box view of the drone, whereas at the system level, the drone was just a black box view. So you can see that this black box and glass box view continue down the levels. The higher level is black box, lower level would be glass box. Ultimately, what we're trying to get to then is this internal block diagram for the drone. This is the detail of the design that I want to be able to hand off to my design team so that they can begin to design the component. This is an architectural view. I can show the different types of components. I can show links and the interconnections, identify that there are different types of links, identify specifics such as ports. We want a very specific connector. It's predefined. I want to carry that forward from a previous program into this particular design. But this is the level of detail of understanding of the components and the interconnects of that system to be able to hand off. And in this case, this was specifically done for a wiring harness and interfacing to the Zuken E3 series tool. And you could identify then with the links, a color of red being power, a color of blue being digital signals, and then communication signals. So that's what you would pass on. Now, I've got a detailed design to a point conceptually, this architecture. How do I start to validate it? So at the systems level, we're really validating the assumptions that we've made. Where you take cost, mass, weight, and divvy it up, that's exactly what we're going to go through. We start by defining parameters. This is how we enable the analytics. Within the video drone system, we have defined a number of them, be it business value, cost, mass, operation time, etc. This is the starting point. As I start to build this reference architecture, I further those parameters as I go down, adding the information that I need for each component in the system so that we ultimately can start to do the analytics. So in this case, the drone, the main battery, and the flight controller all were built out further from the components so that we could get to the analytics. In this case, we take those parameters and we start to build these constraint definitions. This is a parametric diagram where we connect all of those parameters into an understanding of what is that calculation? What is that analysis that I need? In this case, I've taken the drone, specifically we're going to talk about the overall system weight, but I've taken the drone weight as the main block here, and it ties in then all of the components below, each having their own mass. We then roll that up into the system weight, which then takes into account both the drone weight and remote control weight. In this case, I've represented the remote control weight as a single mass rather than the sum of its components, ultimately leading to a video drone system weight. Similarly, we can do that with our business value definition as an external type of calculation that is the marketing model that defines how well this is going to perform given different system designs in the marketplace. So system cost obviously influences the market. System weight, maybe not as much. Particularly in the video drone, the system operating time is a big one, as well as the video resolution. So that is the constraint that can be built up. And then these constraint definitions can be handed off to analytics. So we've gone through and gotten to a point where I have enough detailed design to hand off to the detailed design team and also to the analytics team to start analyzing and validating that my assumptions are correct. At this point, I'm going to hand it off to Alex Luke, who is going to then take us from this analytics and show you what we can do with Model Center.
Perfect. Thank you so much, Steve. Thank you to all of you again for attending this webinar. I would like to start my presentation by sharing this bridge picture with you. It is a famous bridge. I'm sure everyone knows this bridge. Famous or not, bridges are everywhere, anchored in the landscape for many centuries, and we take them for granted. Their importance is fundamental as they connect two places separated by a geographical barrier. You should ask yourself, why am I talking about bridges? Well, you will understand in a minute. In engineering modeling, there are two worlds that have historically been disconnected. I am referring to the world of descriptive system models, GENESYS models, for instance, that capture information about the architecture and design, and the world of engineering analysis models on the other side, all the models engineers build and run to evaluate how a system performs. Our team noticed a lack of connectivity between these two worlds a couple of years ago and decided to develop Model Center MBSE to create a digital engineering bridge between system model and analytical models. To understand how this bridge works and how this bridge creates the ability for users to verify requirement satisfactions and to run trade studies, it sounds important to first describe its two foundations. On the left side, you have the system model. This is what Steve focused on during the first part of the webinar. This foundation is doing a great job supporting system description, structure, behavior, and requirements. Let's focus on the right foundation then, what I called Model Center engineering analysis models. With Model Center, you can automate just about any engineering tools, and we give you the tools to do it yourself. We are vendor neutral, so there is no limitation in the tools you can integrate and automate in Model Center. Let's consider a simple model that you developed and you would like to automate and integrate with other models. It can be any tool you would like. So we have a small representation of the solution that you can automate with Model Center here. It can be CAD tools, CFD tools, FEA tools, cost analysis tool, MATLAB, Excel, or your old Fortran script if you would like. What Model Center does is that it puts a light wrapper around your model. It gives you the choice to expose the input values you want to have access to later here on the left side. And you will be able also to select the output values that you would like to expose because they are KPIs or because they will become inputs in downstream components. And finally, Model Center is automating this whole process. So essentially, and I will focus on this notion, we created a kind of black box that we can pass inputs to and that will automatically generate outputs. So once we have these automated models in Model Center, which can be stored and reused for different projects, we'll use them to create a workflow, as you can see here. You can think of a workflow as a flowchart in which the models will be executed in a specific order. So the outputs of the first models will become inputs into downstream models. These workflows can be as detailed as it is required for them to capture all of the steps that you're currently going through with the manual process. One interesting feature that I will mention here is that all of the models that you're integrating in Model Center don't have to be located on the same computer thanks to Model Center remote execution. You can basically run the analysis on HPC or remote servers, which will ease basically the collaborative work between your teams located in different cities in the world. Now that I gave you an overview of the Model Center integration capability briefly, I would like to get back to our video drone system example that we developed together with Steve. So in the first part, Steve defined the requirements and architecture of the video drone system using GENESYS and created simple constraint definitions to evaluate some characteristic of the drone. I then used Model Center to create more complex workflows to compute the force, the mass, the power, the costs, and the business value associated to a given drone design. So here on the right-hand side, you have a really simple workflow that I came up with. It's composed of just 4 basic Python scripts. And the aim here is to compute all of the forces that are applying on the drone during a cruise flight. So this is still a complex model. I mean, we have different scripts. We could have used much more complex tools. We have dedicated plugins for that, but I won't deep dive into technical details, not the goal of this webinar. But Model Center is giving you the possibility to package up this complicated workflow. So you will create a kind of black box, and you will be able to lower the number of variables that you decide to expose. So Model Center gives you this opportunity to package up your workflow. I would like to connect this analysis to the system model in GENESYS while hiding its complexity and filtering out irrelevant variables that have not been defined in the GENESYS model, for instance. Now that we focused on both foundation of the bridge, it's time to explain to you in details how does the connection work. So we have our left foundations here. So it's the system model in GENESYS. So we can see here the structural diagram, the BDD, and then the parameters definitions that Steve mentioned earlier. And on the right-hand side, I showed you how we could use Model Center to automate complicated workflows and to use them as black boxes. So we just define the inputs, the outputs, and the model to run. So here we will have Model Center MBSE user interface that sits in the middle, accessible from inside GENESYS, where you will be able to map your system model parameters with the external analysis variables. And I will show that to you in a demo a bit later. We'll now see how Model Center MBSE allows you to validate the assumptions of conceptual designs and to verify if the requirements are satisfied or not. This is what Model Center MBSE user interface looks like when you open it from GENESYS. So you can see here different sections, 3 of them. When you fire up Model Center MBSE, it will automatically load the system model structure, as you can see here, and the different parameters created by Steve earlier, as well as the list of requirements defined and some analysis. Now the user will be able to import external analysis. So it will basically create a library of analysis available for the system engineer to use. He will be able to select the analysis to be run by a simple drag and drop. He will also be able to specify which requirements he would like to investigate and to make sure they are fulfilled. And here you will see it in the demo. Once you choose your analysis, Model Center will automatically populate the upper section with the parameters involved in the analysis. Input parameters in green and output parameters here. You will also have then the possibility to run the workflow from inside GENESYS, and you will get access to this kind of tab, so the result tab, in which you will be able to see which parameters have gone up or down here, but you will also be able to evaluate the satisfaction of the different requirements here. So you will see a red tick or a green tick, sorry, or red cross, depending on the satisfaction status of the different requirements. So we'll start with a small video here to show you how to verify requirements in GENESYS. So this is an inside view of GENESYS. So this is the joint design that's the system model that Steve created. You can see the different components that he created, as well as the constraint definition he talked about. So here, for instance, I'm focusing on the joint cost. He added a description and a simple mathematical expression. He then described the independent and dependent variables involved in the mathematical expression. And now we'll focus on the parametric diagram view. So here you have the joint cost constraint block that is sitting in the middle, tying in all the components and their parameters. Here you can see two constraint blocks, so it's one level up. You have the joint cost constraint block that feeds into the system cost constraint variable, as you can see here. So you can create connections between the different constraint blocks, and you will see the connection between the different parameters. Here again, you can see the different parameters that Steve defined. So the objective and the threshold for the different parameters for the different components. And I'm insisting on that. Here you have the design column that is left blank at the beginning of the study. So everything is ready for us to use Model Center and MBSE inside GENESYS. So here I'm firing up Model Center and MBSE. We have a plugin there. I'm exporting the constraint definition and the requirements defined by Steve in the system model. You will see here we have access to the system context. So the different layers, so the system, and then for the video done system, we define a bunch of parameters. Model Center automatically created an analysis based on the mathematical expression defined by Steve. And we will also have access to the list of requirements. We can simply drag and drop the analysis that we would like to use. It will automatically populate the upper section with the parameters involved in the analysis. And I will also select one requirement, so the cost requirement, to make sure that my cost requirement is fulfilled. So here I have one given design. I will run the analysis. Model Center will run the analysis in the background, and we will see here the result tab. So we will see the evolution for the different variables, and we can see here that the total cost is exceeding the threshold, so the requirement is not satisfied. I will get back to my execution plan, change and input parameters directly from inside GENESYS, rerun the analysis, and this time you will see that the requirement is satisfied. So we are happy here, and we would like to save this design into the system model. And this feature is available using GENESYS. So we will populate here the design column. As you can see here, we'll push the results back of the simulation into GENESYS to keep track of the different simulations that we are running. In the second video here, I will work with more analysis. So this time I will open an existing file. So it's possible to save execution plans that I created using Model Center and MBSE. And you will see here that the only difference is that I created more analysis. So I connected more external analysis, and I will show to you how I did tie an external analysis to my system model. So I will edit the analysis, and you will see here that I connected to the local host. I could have connected to remote servers. Here on the right-hand side, I have my analysis with the variables that I decided to expose. And on the left-hand side, I have my system model structure. And you can see that I connected the different parameters in the system model to the variable that are exposed in the analysis. So once it's done, I will show to you how we can deal with more complex workflows, so with more analysis using Model Center and MBSE. So here I'm selecting 7 analyses, as you can see, and 3 requirements. So the operating time of the drone, the video resolution of the camera, as well as the total cost to produce the drone. I have more parameters involved here in the analysis. And this time when I push the run button, Model Center is gonna take into consideration all of the analysis and come up with a workflow that enables the completion of all the analysis. And you can see here that out of the 3 requirements, only the total cost requirement is fulfilled, the video resolution requirements, as well as the operating time are not satisfied. So we are in a conceptual phase here, and you can see here that 2 out of the 3 requirements are not fulfilled, and we are not happy with that. So we will need to explore design space to identify possible candidates. And to do that, we will have to export the workflow to Model Center. So we saw together that Model Center MBSE is great to calculate a business value associated to a given design configuration. But if we're not happy with the performance of our system, we will have to export the workflow to Model Center to run trade studies. So you can see here that we exported the workflow to Model Center. We have our different blocks. We have access to the different inputs involved in the analysis. So the battery type, the camera type, for instance, the outputs of the analysis here in the upper section. And also what is really important for the analytics engineer, we have imported the requirements, and we can know directly when we run the analysis in Model Center if the requirements are satisfied or not. So in Model Center, you have access to a set of powerful algorithms suiting all problems configurations to run trade studies. So you can run DOE to explore the design space to find cause and effect relationship. You can also run optimizations and probabilistic studies analysis. And Model Center also contains visualization tools to explore design space. So it's good to have methods and algorithms to run trade studies, but you have to make this data actionable. You have to be able to draw conclusions based on the different analysis that you carried out. So here I selected 2 examples. I set up a DOE to test 8 different configurations, 8 different cameras, and 6 different batteries with different characteristics. So the different parameters, the different components have different power, different cost, weight, and voltage. So here I will show you the first video. So we have a parallel coordinates plot that shows data in multiple axes aligned parallel to each other. So here, the raw data, well, we cannot really draw conclusions based on that. But you can define objectives in the tool. So we want to maximize the operating time of the drone. We want to maximize the video resolution and to minimize the total system cost. We can also define constraints. So we want all of our requirements to be satisfied. And you can see here that some candidates have been grayed out because they are not satisfying all the requirements. Here you will be able to add additional filters. So here, for instance, if we want to minimize the system cost, you can see that the optimal candidate is based on the choice of the camera number 4. Now, if you want to maximize the total operating time of the drone, we will focus on another area of the design space with the camera number 2 and 5. So here to conclude, I have a 3D scatter plot in which I exposed 3 performances that are interesting for us: the video resolution, the system cost, and the system operating time. And I want to show you the trade-offs here in our study. I decided to highlight the Pareto front. So you can see here that if we want to maximize the video resolution, because it's the most important performance for us, we will rather focus on this area in the design space. If we want to minimize the cost, we will rather focus here in the lower right area. With Steve, we defined together what we call a business value definition that he talked about a bit earlier. I will here add a filter, and you can see that I will target one candidate, which looks like to be like the optimal candidate here in our analysis, and I can get access to his parameter configuration. In summary, Steve and I would like you to remember these 3 takeaways following our presentation. First off, the importance of defining a rigorous systems engineering process that you are going to use and use it. So from the requirements refinement to the system context, behavioral and functional development. The second takeaway would be you to remember how does Model Center and MBSE allow you to verify requirements in early steps of your development process by creating a bridge between your system model and simulations. Finally, I would like you to understand the importance of running trade studies in Model Center to understand your design space and to find better designs. That being said, I will hand it over to Jamie for the conclusion.
All right, sounds great. Thank you guys so much. Excellent presentations. The remainder of our event today is going to be the Q&A session. Please use the questions feature on the right-hand side of your GoToWebinar panel. If we are unable to get to your question, or if you have additional questions following the presentation, please do not hesitate to contact us. So it looks like we got some coming in. It looks like we got to put some folks on our, you guys' cameras are off, so I'm going to go ahead and pop those on. All right, so our first question is, can you explain model validation and how it is different than the trade study?
Sure,
I'm not
I'll
sure.
take that.
Sure.
So if you look at the parameters and how we came about filling in those parameters, so at the system level, very much driven by requirements. But as we broke down to our components, that would have been from a group of subject matter experts, from a team, looking at this conceptual design and starting to work through and break down those higher level parameters into lower level parameters. The validation exercise is really about validating those assumptions, because as we broke them down, they're not based on a detailed design, they're based on assumptions of the reference architecture. As we transition from the reference architecture into detailed design, that's where the trade studies come in. The more information I have about the detailed design, the better estimation of those parameters and performance that can be done. So there's a back and forth between the system assumptions and the system concept model and the detailed design.
Okay, great. Next one we have is, how are cost and business value calculated in Model Center? Are they from user-defined models?
Maybe I can start. I can take this one, Steve, and hand it over to you. So we worked together on that with Steve. We used a simple Excel spreadsheet to calculate the business value based on different performances linked to the video drone system. So stop me if I'm wrong, Steve, but I think we started with basically a base volume, so number of drone that we would sell with a given set of designs, with a given performance. Sorry. And then basically we created simple functions to show the relationship between an increase of the video resolution of the camera and the impact of this on the sales of the drone. So we created really simple functions in Excel for the video resolution of the camera, for the total mass, for the operating time, and other performance values. And then we simply created a lookup function. So depending on how the design and the video drone performed, we had an associated business value. And then I just had basically to use our Excel plugin inside Model Center to feed the new set of input parameters into Excel. I was asking Excel to compute and basically to compute the business value, and then the results of the business value was fed into Model Center. But you could have used like more complex tools. I mean, it was not dependent on Excel.
Yeah, and really, when you look at it from the system side of it, you'd be working with your marketing team, your business team, and setting up those rules and that understanding of how does our volume get adjusted as we change different characteristics of the system. What's our business model for taking a product from cost to end value? So they're not something that we would just create on our own. We would work with our business partners to create that model. And it's not just a straightforward model. It is something that we would have to kind of come up with different ways of representing it.
All right, next up, how do you handle data management, more specifically in cases where different people are working on the same model systems?
So data management is a good question. Within GENESYS, the way it is set up, other than and then trying to take on special cases, the model is set up as a collaborative database, which means we can all work on it simultaneously. Now that's quite different than a lot of the developments in, say, software, where we create branches, people work on branches. But there are means of baselining the model, distributing the model, and allowing for changes on branches, if you will, and merging the information back together. But the primary idea behind GENESYS is that it's a collaborative environment where we're working on the data real time together.
Can you provide some thoughts on how to best get started with a transition to model-based tools? For example, if we are starting a new product from scratch, what strategies might we deploy to implement MBSE/MBE?
Well, David, I think this one is for you.
Thanks for that, Alexander. So the first, I'll warn you first with a trap. And the trap is to adopt what you've read in a paper, adopt something that you have seen for somebody else. And the reason that is a trap is good systems engineering, good model-based systems engineering, good MBE is always fit for purpose. So the first place to start is actually to ask yourself, what are you trying to get out of this? Are you trying to get better knowledge management and retention? Are you trying to feed analysis? Are you trying to feed detailed design? But if you don't begin literally with your set of requirements and then look at how you map your new activities supported by a tool, you can do a lot of work without necessarily advancing your business objectives.
Great. If you have to apply this process to a component subsystem, would you still have to model the full system? For complex systems, the area of our group's responsibility is limited, while there are still top-level system requirements that get impacted both ways.
So the answer is, it's a good question. The answer is no. You can define whatever scope that you wish. So you could define your component of interest, your subsystem of interest, as the focus of your engineering effort, and then feed the results outward. You might have a lightweight skeleton of the greater system so that you ensured that you had an understanding of all your interactions, all your interfaces, but you could limit your focus only to the component or subsystem of interest.
Yeah, to add to that, David, and maybe from the presentation, when I talked about that system context, right? It makes sense at a system level. At a component level, you'd be creating a similar system context. It would be your component as the system of interest, and then whatever else in your system that it's interacting with.
You connected to more detailed design tools for analysis, but what about for actual design at the lower design level to create software, for example? Are you expecting all design detail to be captured in the SysML system model?
You want to take that one, Steve, or you want me?
I'll let you take that one.
Okay, so the answer is no, we're not expecting that level of detail to exist at the system level. It's very important in model-based to actually stay at your level. The tendency of engineers is actually to go too deep and cross into the other space. So what you end up with is, on my meta model chart on the right-hand side, I had the fundamental definition of architecture. What are the parts? What are the interconnections? What are the connection surfaces? In our language, components, links, and ports. The lowest level of the system model becomes the highest level detailed design model. In the example of Zuken E3, a wiring harness, what happens is we push that low-level model across so that you have a top-level electrical schematic, which the electrical engineers then continue downward into a good detailed engineering design. They can always link backwards to the system model, to the requirements, to the functions, etc. That pattern holds, whether you're talking about mechanical, whether you're talking about software, whether you're talking about something else. So the lowest level system physical architecture becomes the highest level detailed design framework, which is then fleshed out in a lower level tool, digital connectivity, then across the thread.
All right, thanks, David. How does GENESYS extract the constraints and requirements information contained in the system model in order to validate a design configuration in Model Center MBSE?
Maybe I can take this one. So if you consider the requirements, when you define a parameter requirements, you will define a threshold and an objective. So here we are simply considering simple comparison analysis. So my performance has to be greater than a given value or lower than a given value. When you fire up Model Center MBSE, I've been a bit quick on that during the video, but you have the possibility to export the requirements and constraint definitions created in the system model. And what it will do, it will create simple scripts that will be saved in the analysis path. And when you will fire up Model Center MBSE, they will appear in the list of analyses that are available. So when you will select this requirement, Model Center will consider the simple script generated by GENESYS when we fire up Model Center MBSE. It will be a simple comparison, so it could be a Boolean. So the results of this comparison is either true or false. Model Center will compute that and display the results in the result tab inside Model Center MBSE. So this is how it works. And maybe David or Steve, you want to mention the small modification that came with GENESYS 2021. I think you have another interface now for the parameter definition in which you can be more precise. You can define not just an objective, a threshold, but a minimal and a maximal value. So bounds, an interval for each parameter.
Yeah, there are a couple of different aspects in that conversation. Jamie, when you stated the question, I'll start with the idea of how do we do this? Well, GENESYS is designed as an open architecture type of framework. Fundamentally, underneath the GENESYS client is a database and services function in a SQL database. There is a set of API that have been developed in terms of a C# programming language that will allow anybody to access the data through a developed piece of software. And so that's essentially how Model Center, Phoenix Integration, and Vitech jointly worked on that interface. We helped with the understanding of the APIs. The Phoenix Integration team worked on the user interface. We collaborated to create that connector. Now, relative to your comment on GENESYS 2021, there is a change to parameters. What you saw in the presentation was GENESYS 2020 R2, our previous release. We now have GENESYS 2021, and we've taken parameters, and there's kind of two things we've done to it. That objective and threshold has now been turned into min, objective, and max, which gives you the ability to put ranges on those parameters. And then we have the design value and essentially a tolerancing on that design that we can capture. And then your measured values. We've also taken parameters and allowed for binding of that parameters across multiple entities in GENESYS. So if it's a parameter that's tied to a requirement, it's the same value then that's tied to your component or your function or your verification information. So that parameter binding allows you to have the information in one place and maintains it across the entire model.
Great. I think we have time for just a couple more. Which tool owns the data, such as parameters between GENESYS and Model Center?
GENESYS is the source of truth on the parameters from the requirements view. If you looked at, as we talked about, that objective and threshold, these are your design targets. Model Center, then we would pass that information off. the analytics then come back and provide your design values. If there's a conflict there, the total team would sit down and resolve those conflicts between parameters to decide, do we need to update the target, or do we need to continue to refine the detailed design?
All right, let's do one last one. Is it possible to create complex requirement analysis more than a simple comparison analysis to be run in Model Center MBSE?
Yes, it is. So here I was just showing the simple requirement verification process. You can come up with more complex scenarios. You can write your own script inside Model Center MBSE in which you can not just use comparisons, but more complex scenarios with if loops, depending on the values of certain parameters, for instance. And this is feasible inside Model Center MBSE. So yes, you can come up with your own more complex requirements analysis. That's possible.
Thank you very much, Alex. I think this will conclude our Q&A portion for today. I would like to thank everyone for joining us for this event, which is part of our 2021 virtual event series. You can find more information on the Phoenix Integration website about upcoming events. On the screen here, we have upcoming MBSE workshop, an MDAO webinar, and an MDAO app demo that will take place in July, and we hope you will join us for some of these events. And finally, I would like to thank our presenters, Mr. David Long, President of Vitech, Mr. Steve Cash, Principal Systems Engineer of Vitech, and Mr. Alexandre Luke, Application Engineer, Phoenix Integration, and ANSYS Company.
Thanks,
Thank you so
Jamie.
much,
Always a
Jamie.
pleasure.
Thanks, Jamie.
And finally, I would like to thank our audience for attending. This concludes our MBSE partner session. Enjoy the rest of your day.